Today we'll discuss the closed system or non-flow work. Here there is a piston cylinder arrangement is there having at a pressure P, and the displacement of the piston is Tx. So the pressure is equal to force divided by area. Force equal to pressure into area. The work done by this process W equal to force into displacement. So del W equal to force into dx. From that we can find that force equal to pressure into A, that is the area, and then dx. So that is the volume. So the work done is equal to integration of P dV. P is the pressure, R dV is the change in volume. That is the closed system or non-flow process work. And we can say that by plot also, if there is a diagram with respect to pressure and volume, there is a state 1, a process is taking place from state 1 to state 2. The area under the curve, when it projected on volume axis, it gives the non-flow process or closed system work. That is the area under the curve, when projected as volume axis, it gives closed system work. Now we'll discuss what will be the work in various processes. There are 5 processes. First one is the constant volume process. In constant volume process, what will be the closed system work? Constant volume is there is a container is there and having some gas. The volume is constant. So closed system work is W equal to integration P dV. So V equal to constant, dV equal to 0. The work done will be 0. And from the diagram you also can show that if the constant volume process, then the work done will be 0. The area under the curve will be, there is no area under the curve from state 1 to state 2. Okay. The second one is the constant pressure process. Second one is the constant pressure process. Constant pressure process means there is a piston cylinder arrangement is there, and the displacement of the piston is taking place due to some pressure, and you can assume that it is a constant pressure process. Displacement, this one is the displacement, that is the x. Okay. So now the work done in constant pressure process, integration P dV, that is from volume 1 to volume 2. You can show also from the diagram, if there is a state 1 and state 2, state 1 and state 2, there is a pressure and there is a volume, and this is the process is taking place, but it is not constant pressure process, so you have to omit this. There is a state 1 and state 2, and process is taking place from 1 to 2. That is the change in volume for the process. That is, assume that V1, that is V2. So from limit V1 to V2, P into dV. So pressure is constant, taking outside, it will be V2 minus V1. That means P into V final, that is the final volume, minus V initial. That is the constant pressure process, what will be the work done. Now we go for the what will be the work done in case of isothermal process. Now we go for iso. Isothermal process or constant temperature what will the work done for isothermal process or constant temperature process? Work done equal to integration P dV. The plot for the isothermal process in PV diagram will be rectangular hyperbola. From state 1 to state 2, there is a process is taking place, and this curve is called the rectangular. This is the rectangular hyperbola. From the ideal gas equation, we can write that PV equal to mRT. So temperature is constant, that means PV equal to constant. That means P1 V1 equal to P2 V2. That means V2Y V1 equal to P1 by P2. Now we find what will be the work done in that process. Work done equal to integration P dV. The PV equal to constant, that means constant wise V into dV, and the initial volume is V1 and the final volume is V2. So this will be C ln V V2 by V1, C ln V1 V2 minus ln V1. So you can write that C into ln V2 by V1. That means you can also write then constant equal to PV, that means MRT, P1 V1 ln V2 V1, or you can also write that MRT ln V2 V1. Okay, and also you can write that work done equal to, you can also write that work done equal to MRT ln P1 by, that is P2. That is the work done for the isothermal process. Okay, now we go for the adiabatic process. Number 4 is the adiabatic process. In adiabatic process, the heat transfer is 0. In adiabatic process, the heat transfer is 0, and the definition of the process is PV to the power gamma equal to constant, where gamma is the adiabatic index. And the standard value of gamma for air equal to 1.4, standard value of gamma for air. Okay, now we have to find out what will be the work done in case of adiabatic process. Gamma equal to constant, pressure equal to constant divided by V to the power gamma, or you can say that constant into V to the power minus gamma. V1 to the power gamma equal to P2 V to the power gamma equal to constant. Okay, P1 equal to C V1 to the power gamma, P1 equal to C V1 to the power minus gamma, V2 equal to C V2 to the power minus gamma. Now we can have to find what is the work done in that case. Work done equal to integration, what is the initial volume, that is V1 to V2 into pressure into change in volume. V2 divided by V1 C, that's P equal to C into V to the power minus gamma into dV. Now you have to take out the C, V2 by V1 V to the power minus gamma into dV. So work done will be C V to the power minus gamma plus 1 divided by minus gamma plus 1 whole to the power V2 divided by V1. So C minus gamma plus 1 V2 to the power minus gamma plus 1 minus V1 to the power minus gamma plus 1. Okay. Now from that we have to write that this is our last equation. C work done equal to, this is the last equation. From that we have to write again C minus gamma plus 1 V2 to the power minus gamma plus 1 minus V1 to the power minus gamma plus 1. From that you have to write here work done equal to C minus gamma plus 1 V2 to the power minus gamma into V2 minus V1 to the power minus gamma into V1 1 by minus gamma plus 1 multiplied by C into V2 to the power minus gamma into V2 minus C V1 to the power minus gamma into V1 equal to 1 by minus gamma plus 1. That means C V2 to the power minus V2 to the power V2 to the power minus gamma, that is P2. So P2 V2 minus P1 V1. From that you can write that P1 V1 equal to C V1 to the power minus gamma, that is the work done. So from that we can write that work done equal to P1 minus V1 divided by minus P2 V2 divided by gamma minus 1. That is the work done for adiabatic process. Okay. Now we will discuss what is the work done for polytropic process. The last one is the polytropic process. That means PV to the power n equal to constant. N is the polytropic index. N equal to polytropic index, and the value of the n lies between greater than 1 and less than gamma. Okay, so from that you can find that we can find the derivation will be same as adiabatic derivation. So I just write the what will be the work done. In case of adiabatic process, the work done equal to P1 V1 minus P2 divided by gamma minus 1. This is the work done for adiabatic process. Gamma is the adiabatic index. You just have to replace the gamma with n for the work done in case of polytropic. P1 V1 minus P2 V2 divided by n minus 1. N is the polytropic index. You have to just replace. Okay, these are the work done in case 5 cases. Now we will discuss, there are some points with respect to, important points with respect to work done. Some important point with respect to work transfer. Number 1, it is a path function. It is a path function. That's why the work done by a process is depend on the area under the curve. That is, the what will be the path taking place from 1 to 2 is depend on the area under the curve. If the curve is like that, in this case the work done is also area under the curve. For that curve, the work done will be area under this curve, but for this curve the area will be this plus this area. So with respect to pressure and volume, it is a path function. First point, work should cross the boundary. That means if there is a system is there, and there is surroundings is there, the work transfer will be taking place only it should cross the boundary. That is the boundary. Okay, work transfer taking place if it crosses the boundary. Okay, these are the important points with respect to work transfer. And there are some points when we apply the work transfer W equal to integration P dV. When we apply this, there are some points. When we will apply this equation, there are some conditions when we will apply this equation. The process should be a closed system, or it should be a closed system. The process must be a reversible process. The process must be reversible process, and work should cross the boundary. We will apply this equation W when it is a closed system and the process is a reversible process and work should cross the boundary. Then we can apply W equal to integration P dV. In the first law of thermodynamics equation, from that we can write that in the first law of thermodynamics, the work done, here we see the work done del W equal to P dV. Del W equal to P dV. That is the path function, that why there is a cut is there. This is the work transfer is a path function. From the first law of thermodynamics, we can write that first law of thermodynamics we can write that del W equal to del Q equal to du, what is the change in energy, dE plus del W. This is the heat transfer is also a path function, and work transfer is also a path function. And the energy, this is the point function. That means the heat and work transfer are dependent on the path and is dependent on the state. That is the point function. What is the energy? Okay. Thank you.